Hello students, this is Mr. Allen, and today we're going to look at section 5.3, which is on separation of variables. We have two objectives today. Today we want to be able to recognize and solve differential equations that can be solved using separation of variables. And number two, we want to use differential equations to model and solve applied problems. Consider a differential equation that can be written in the form m of x plus n of y dy dx equals 0, where m is a continuous function in x alone and n is a continuous function in y alone. As we have seen from these types of equation, all x terms can be collected with dx and all y terms can be collected with dy, and the solutions can be obtained by integration. Such equations are said to be separable, and the solution procedure is called separation of variables. Below are some examples. Let me move that out of the way. Below are some examples of differential equations that are separable. So if we look at the one on the left, you've got dy over dx equals x divided by y squared plus 1. You'll notice that here we have x's and y's on both sides of the equation. But if we cross multiply, we can get the equation on the right. Now notice, here's the key idea. Notice that everything on the left now is in terms of y, and everything on the right is in terms of x. So we would say that this is a separable equation. This is a crucial step when it comes to solving this, is actually separating the variables. Let's just look at one more example here. Let's look at this third example here. We have sine x y prime equals cosine x. Now keep in mind that y prime is the same thing as dy dx, and we're going to use that in our examples here in a few minutes. Notice that we've got x and y variables on both sides. Now, in this particular example, there's only an x variable on the right, but there's also a term with an x variable on the left. Not to mention there is a dx on the left. Again, what we can do is we can go ahead and separate those variables. And I would like to note that cosine x divided by sine x is cotangent x when we multiply the dx to the other side, and then we're left with dy. So notice now, again, we have all the y terms on the left and all the x terms on the right. So these are some examples of separable equations. So now let's look at this particular differential equation. On this differential equation, you'll notice that we have y prime, and x on the left and just 0 on the right. The first and most important step for us to do in this problem is to separate our variables. So I'm going to go ahead and work this one out manually. I'm going to try to do the other examples in this presentation with already pre-made type notes so that you guys don't have to try to read my writing. But what I'd like to note right here is I'm going to change this y prime to dy over dx. That's going to help me in my mind make sure I understand where the x terms are and the y terms. So now we can see that we've got x and y terms both on the left. So the first thing we could do is just multiply both sides by, add x to both sides. In other words, move that minus x to the right. Notice now we still have a dx on the left-hand side. So now we're just going to multiply that to the right-hand side. And so you're going to get x dx. Now we have our differential equation written in it with the variables separated. And so now the next key step is to integrate. So now we are going to integrate both sides. When we integrate both sides, we're going to get y squared plus c1 equals y squared over 2 plus c1 plus x squared over 2 plus, and I'll call it c sub 2. And that just means another constant. As we've seen in previous lessons, we can combine the c1 and c2 to make just c. So then this is going to give us something like this. And I'm going to do this a little bit differently. I'm going to add or subtract the c2 from the right, and then I'm going to bring the y squared over 2 to the left, so that's going to be minus. Now I'm going to multiply both sides by 2. Now when I multiply both sides by 2, c still stays as c, and we're going to get our final answer here, which is going to be x squared minus y squared equals C. That is the general solution for this particular differential equation. So now I'm going to ask you a Algebra 2 pre-calculus question. What kind of curve is that going to generate? So our general solution here is x squared minus y squared equals C. If you were to put this differential equation into Wolfram Alpha and hit solve, it will give you this solution here. So what it's doing is it's isolating this y. So this would be negative y squared equals, and then you'd over here on the right, you'd have negative x squared equals, oops, I'm sorry, not equals, it'd be plus C. Sorry about that. That would be plus C. And so then you would multiply through by a negative, and you get x squared plus C, and then you would square root both sides, and then remember, when you square root, you have to do plus or minus. So this is now, we've solved it for y. That's what we've got here if you look it up in Wolfram Alpha, which is equivalent to the way we wrote it here, which is in what we call implicit form. This is more of the function written explicitly, and it's technically not even a function. And I'm going to get to what this is in a second. Now, let's say you didn't know how to solve this using the separation of variables, and you just graphed the slope field. Here's what the slope field would look like. Does this give you any idea of what this equation is going to be the solution? Well, here would be an example, and I just let C equaling 1 in this example. You can see that we have a hyperbola. So the general solution is their hyperbola. So there you go. That's example number 1. Again, the bulk of this problem I did on this slide here. I just wanted to kind of connect this back to what we did in sections 5.1. Let's look at a little bit more complicated example. This one I'm not going to write out by hand. I've already got it typed in here. It says find the general solution of x squared plus 4 times dy dx equals xy. Now in this example, you can clearly see that we've got x's and y's on both sides of the equation. So we're going to need to separate. And let me make sure I emphasize this. The very first step is to get all the x's on one side and all the y's on the other side. On the AP exam, that one point gets you in the game. And so what I mean by that is if you do not do the separation of variable first, you will get 0 marks for that on a free response problem. So it is the most important step. So to begin, note that y equals 0 is a solution if you put 0 in for y. To find the other solutions, we'll assume that y does not equal 0, and we're going to separate the variables. So the first thing we're going to do here is we're basically going to cross multiply, and we're going to get dy over y equals x over x squared plus 4. This is going to be a nice review of some of the things that we've already been looking at. Now we're going to integrate. So we've got dy over y, we're going to integrate that. And on the right-hand side, we're going to integrate x over x squared plus 4. Hopefully you recognize on the left that that's going to be a log integration, as is the right, but we're going to do a little bit of u sub there. So you're going to get the natural log of the absolute value of y equals 1/2 the natural log of x squared plus 4 plus c1. Remember, we have an x logarithmic property that if you have a constant times a logarithm, you can make that the exponent. So this would become the exponent of that. So that would be the square root. Now we can raise both sides to e. So basically what we're doing here is we are eing both sides of the equation. I just raised both sides to the power of e. I'm sorry, you're taking e to the power of whatever's on the left and the right. So that gets rid of the natural log on the left. Now e to the c sub 1, what's e to the c sub 1? That's just going to be c. Now the plus or minus here comes from these absolute value symbols. So our general solution is as follows. Now guys, this was a much more complicated example. That's why I went ahead and just had it typed in here for you. So let me go back one slide. This integration led us all the way down to here. Notice that the plus or minus and the e to the c sub 1 just became c. C is an arbitrary constant. It could be positive, it could be negative. That's why I don't need the plus or minus. And it could be e to the second. That's still just a constant. All right, so final example here today, we're going to look at an application. This one's on wildlife population. Says the rate of change of the number of coyotes N of t is, in a population is directly proportional to 650 minus N of t, where t is the time in years. Where t is equal to 0, the population is 300, and when t is equal to 2, the population is increased to 500. Find the population where t is equal to 3. So this is kind of a typical problem that you might see. Now I'm going to underline the key information here. The real key information is that it tells us that it's directly proportional. Since it's directly proportional, that means we get the following differential equation. This is review back from section 5.2. Section 5.2 tells us that the derivative is equal to the constant k times whatever the expression is here. But this time the expression is a little bit more complicated than just a variable. It's not, it's not variable, it's 650 minus a variable. So this is going to require a little bit us to be a little bit more careful. We're going to need separation of variable on this one. We did not need that in section 5.2. So I'm going to multiply both sides by dt. Now I'm going to divide by 650 minus n. Now we have our variables separated. On the left-hand side, everything's in terms of n. On the right-hand side, everything's in terms of t. Note that k is a constant. Okay, that constant is k. Now we'll go ahead and integrate. Of course, the left-hand side we get using natural log. Notice that that negative is there. That negative is there because of the u substitution. On the right-hand side, this is just a constant a constant dt. So that's just going to be a linear integration. So kt plus c1. Now we'll go ahead and multiply both sides by negative. Now we're going to go ahead and raise both sides to e. And now we can just subtract the 650 and then divide by a negative, and we get our general solution, which is 650 minus CE to the negative KT. So this should look very familiar because this is something similar to what we did in our section 5.2 notes. Now, we were given the fact that when n was 300, when t was equal to 0, so that means that we can plug in to this general solution here. We can plug in n equals 300, so we would put a 300 in for n, and then t would be equal to 0, so we would put t equals 0 there. So that's going to make that e to the 0, which is just 1, so you can clearly see that C1 is going to be 650. We were also told that when t was 2, that n was 500. So now we're going to substitute that information into our equation, and we're going to find out that k is approximately 0.4236. So the model for our coyote population is given by this equation here. This was the, let me go back one slide here. This was the general solution. This is the, if you will, particular solution. Now we can go ahead and find out what the population is going to be when t is equal to 3. We put t in for 3, or 3 in for t, and we'll get approximately 552 coyotes. So you could probably see how this would be applicable in a biology study or something involving, hunting, or not hunting, but nature preserves and things like that. Here would be the graph of this particular general or particular solution. As you can see, it is growing. It's a growing function, but it's a logarithmically growing function. And then it actually reaches something, the highest it can reach is 650. There's a horizontal asymptote for this graph right here at 650. I'll kind of try to draw this with my finger. That graph will never get above 650. And that 650, you guys may have heard of this term before. That's what we call the carrying capacity. So anyways, that ends this presentation on separation of variables.